Today, we'll do the comprehensive review of operators that can be used when Arduino programming. Quick interruption. This video may be the first video in a series covering basics of Arduino programming, being a part of my larger plan to introduce as many people to Arduino as possible. But you have to let me know whether you like it or not, because in the past I created a video with a beginner's guide to Arduino, and that video did not get a lot of traction. So if you enjoy this content, let me know and there will be more videos like this coming your way. And now, back to the video. Before we start, I have a quick update for you. This month, I got not one, not two, but 3 new patrons. Guys, thank you so much and welcome on board. Support like this means the world to me. For all of you watching, you can support the growth of my channel by joining these guys. Okay, back to our topic. Today, we'll do the comprehensive review of operators that can be used when Arduino programming. There are several types of them: arithmetic, comparison, Boolean, compound, and last but not least, bitwise operators. This video is meant for people who are starting their journey with Arduino programming, so some of the operator types are very straightforward, and I would breeze through them. But some may not be as obvious, so check this video till the end. Maybe you will learn something new. Let's start with the easiest arithmetic operators. First one is a sign operator. This one is used to assign a value to a variable. If you see this operator in between two variables, it does not mean those variables are equal to each other. It assigns the value from the variable on the right to the variable on the left. Then you have add, subtract, multiply and divide operators. And finally you have operator that returns the remainder from the integer division. We will look at this one more closely. Quick presentation in Arduino code. Let's introduce two variables a and b with subsequent values 2 and 4. We open serial monitor. Let's look at the assign operator first. If I send the current value of variable a to serial monitor, the value 2 would be output. And then when we assign the value of variable b to variable a and run the print function again to output variable a, we get now value 4. Now let's reset values of a and b back to 2 and 4 and run few print commands to output results of formulas using arithmetic operators: addition, subtraction, multiplication and division. All results are as expected. We have one arithmetic operator left to discuss: remainder after division. If you need to be reminded what remainder operator is, remainder is the amount left over after performing the division. So for example, we cannot divide 10 by 3. The closest number you can divide by 3 is 9. So if you have 3 times 3 plus 1, it makes 10. And the 1 here is the remainder. This one I actually used to optimize the code in one of my projects. I had video in which I was showing how to control 4-digit 7-segment display. In it, I had an easy sketch that was counting from 0 to 9999. So here you can see how this was working, and here is the code behind it. I created a for loop that was changing the value of variable I from 0 to 9999. I created fairly complex formulas to dissect each value of I variable into digits representing ones, tens, hundreds and thousands, and using setDigit function to output those digits in the right places on the display. We are not going to redo the prototype for this project. We can alter the code to output the results of the formulas into the serial monitor. This way the prototype would be simplified to just Arduino connected via USB to the PC. Simple. Let's glance quickly at how those formulas worked. Let's choose the sample number from the counter range, e.g. 1549. Let's see how the calculations would look like to come up with a digit representing thousands. Here is the calculation for the digit representing hundreds. Is it complicated? You betcha. I spent a fair amount of time to come up with those formulas. I will leave you to check if the other two formulas would work as well. Let's see how this code works. Great. That is what we wanted. But then I realized I can use the remainder after division operator here, and I came up with this code. Let's look at it and dissect the same sample number. Starting with digit representing thousands, the calculation for that digit would look like this. Now let's see how the calculation would work for a digit representing hundreds. Here I will also leave you to make calculation for the two remaining digits. The code is more clear and much easier to understand. But will it work? Let's give it a spin. And as you can see, it does. Now let's look at the comparison operators. There is a handful of them. We have equal to, not equal to, greater than, less than, greater than or equal to, less than or equal to. We mostly use those operators in conditional statements like if, while, for, switch. Let's do a quick demonstration. To be able to do this, I built this simple Arduino circuit. In it, we are using Arduino Nano, 6 LEDs. I'm using those LilyPad LEDs, which have already built-in current limiting resistors, connecting minus of each LED to ground and plus of each LED to digital pins from D2 to D7. Then I have potentiometer connected to one of the analog pins. And finally, I have a 7-segment display to track the current position of the potentiometer. I have a separate video where I show how I build this display. Please check it out. Having the circuit in place, we can now write the code that will demonstrate how those comparison operators work. We start by introducing variable p that will store the potentiometer reading. In setup, we need to set up all the Arduino digital pins to which the LEDs are connected as output. In loop, we use analog read function to read potentiometer value that is in range from 0 to 1023 and use map function to map it to the range from 0 to 9. We save the mapped value into variable p, and then we create a set of if statements, each one controlling a single LED. So turning it off or on depending on the condition being fulfilled or not. So we will turn on the first LED if the potentiometer is in position 5. We will turn on the second LED if the potentiometer is not in a position 5. We will turn on the third LED if the potentiometer is in position higher than 5. The fourth LED would lit if the position is lower than 5. The fifth would lit if position is greater or equal to 5. And finally, the sixth LED would turn on when it is smaller or equal to 5. The code is already loaded. Position is 0 and the LEDs 2, 4 and 6 are on. Because position is not equal to 5, it is smaller than 5 and it is smaller or equal to 5. Let's change potentiometer position. So far no change. But when we get to position 5, now LEDs 1, 5 and 6 are lit. As position is equal to 5, position is greater or equal to 5, and position is smaller or equal to 5. Carrying on, we change position to 6, and now 3 conditions are met. Position is not equal to 5, it is greater than 5, and greater or equal to 5. Further increasing of the pot position does not result in any changes. Now when we return to position 0, you see the LEDs react accordingly. Now let's look at Boolean operators. Comparison operator allowed us to check a single condition. Boolean operator lets us connect several conditions and build more complex ones. We have 3 Boolean operators. Logical AND operator. Here is the alternative notation for it. If both the operands are true, then the condition becomes true. Next one is logical OR operator. If any of the 2 operands is true, then the condition becomes true. The last one is logical NOT operator. We also can use this notation, used to reverse the logical state of its operand. If the condition is true, then logical NOT operator will make it false. We can reverse a single condition, but we can also apply this operator to more complex conditions as well. Let's look at the example. Here is the axis that shows all possible positions of the potentiometer from our example. So 0 to 9. If we have a single condition, p is smaller or equal to 7, this condition will be met in the highlighted range. Let's look at a different single condition. P is greater or equal to 2. that condition is fulfilled in this range. Now if we use logical AND operator to build more complex condition, we can single out positions that are both greater or equal to 2 and smaller or equal to 7. Let's do the similar example for logical OR operator. This condition would help us to select all positions smaller or equal to 3, and that one will select all positions that are greater or equal to 7. And here is the complex logical statement, which is using logical OR operator. This way we are selecting all positions smaller or equal to 3 or greater or equal to 7. Now that we have that complex logical statement, let's introduce the third operator, logical NOT operator. It reverses the state of our condition, so we get the set of positions that are greater than 3 and smaller than 7. Please mind that positions 3 and 7 are excluded. So let's create sample code that will have several conditions using both Boolean and comparison operators and see how this affects our 6 LEDs behavior. So the setup function would be just like in our last example. In loop, we will create several conditions to control the 6 LEDs. The first LED would lit when P would be either 5 or 6. The second LED would be on when the P is larger than 3 and smaller than or equal to 6. The third condition is met when P is smaller than 3 or larger than 6. The last 3 LEDs would be controlled by the same 3 conditions we have just created, but reversed with logical NOT operator. So now, let's load the code and see if it is controlling the LEDs in line with the programmed-in conditions. At the start, at the position 0, we have LEDs 3, 4, 5 on. As P is smaller than 3 or larger than 6, P is not equal to 5 and 6, and P is not larger than 3 and smaller or equal to 6. I will slowly go through all the other positions and you can check if LEDs are behaving as expected. Please note that since we applied the logical NOT operator to conditions 1, 2, 3 to create conditions 4, 5, 6, the first LED always has a different state than LED 4. Same with sets of LEDs 2 and 5 and 3 and 6. Looks like it works just fine. Let's move now to bitwise operators. Here they are. To present how they work, I would use 2 sample variables. Here you can see their decimal and binary representations. First, we have binary AND operator. It copies a bit to the result if it exists in both operands. Here is an example. 2 ones make a 1 for first bit, 2 zeros make a 0, 0, 1 makes a 0, and we carry on like this for all remaining bits. The result is 65. Next is a binary OR operator. It copies a bit if it exists in either of the 2 operands. So here, 2 ones make a 1, 2 zeros make a 0, 0 and 1 make a 1, and so on. The result here is 93. Next one is binary XOR operator. It copies the bit if it is set in one of the operands, but not both. So 2 ones make a 0, 2 zeros make a 0, but 0 and 1 make a 1. We populate remaining bits to get the result of 28. Moving on to binary NOT operator, which is flipping bits. So 1 becomes 0, 0 becomes 1, and so on. Applied to decimal 81, we get decimal number 46. The last 2 are probably the most interesting ones. You have binary shift right operator. It shifts all the bits of the operand to the right by the specified number of positions. Here we take the binary representation of number 81 and we shift all the bits by 2 positions to the right. We are losing data from 2 far right bit positions. This operation returns 20. Then we have also a binary shift left operator. It shifts bits of the operand the same way but to the left. Again, let's apply it to number 81 and shift all the bits 2 positions to the left. The result here is 324. Are you wondering what those bitwise parameters can be possibly used for? Let me show you one example. In my recent video, I was controlling this LED matrix. One of the things I did was to output text on it. It looked like this. And here's the code behind it. Here is the table that holds the text to be displayed, where each cell corresponds to one LED on the LED matrix. As you can see, this is an array of bytes. In loop, I had a nested for loop that was going through all the cells of that table. If cell was holding 1, we were lighting up the corresponding LED. If it was 0, LED was off. Here also we are not going to recreate this setup, but rather alter code to output the result to serial monitor. So we get rid of the two lines that were interfacing with the LED matrix and introduce the line that would output @ in case of 1 and dot in case of 0 to the serial monitor. Let's add a short delay so we can observe how the text is displayed one sign at a time. After processing all 32 cells of each row, we need to send the new line command to move to the next row. Let's load the code and observe the result in the serial monitor. Looks great. Let's take a closer look at the table. This is not the most optimal way to store information. To store info for a single LED or character displayed in the serial monitor, we need just one bit, and here we are using the whole byte, so 8 bits to do it. The optimal way this table should look like is this. Unsigned car data type comprises of 4 bytes, so 32 bits, so perfect for what we want to do here. At first glance, you may not see the text we want to display hidden in that table, but believe me, it is there. But how can we navigate within the bits of those 8 entries in the table? Here is our table. We'll go row by row. In which row we'll try to extract bits starting from the most significant on the left and move to the least significant on the right. But how? Here is where bitwise operators would come in handy. So we have our row of bits. We would introduce shift variable which holds binary value. Initially, this variable will have 1 in the most significant bit position far to the left. Here we will be displaying the results of the bit extraction. So the procedure would look like this. We apply binary AND operator to processed row and shift variable. It carries only the far left bit, in this case 1. All remaining bits of the results are set to 0. Then we shift the bits of the result 31 positions to the right, and we end up with a single bit which was extracted from the far left bit in the processed row. We can now use print command to print it. If we want to extract next bit in sequence, we have to shift bits in the shift variable 1 position to the right. Now if we again use binary AND operator, the second bit gets carried forward. We have to now shift it by not 31 but 30 positions to the right. The bit, in this case 0, is extracted and ready to be printed. We continue the same way to extract all remaining bits in that row. Let's make changes so that the procedure we just explained is reflected in the code. We declare shift variable. Before we start processing each row, it is set to initial value where far left bit is set to 1. We need to change if statement, so instead of reading single value from the table, it actually extracts the bit from the currently processed row. I changed the characters displayed in case of 1 and 0 detection, so the output would look slightly different this time. After extracting and printing each bit, we are shifting all bits of the shift variable 1 bit to the right. This way we will be extracting next bit in sequence. Let's see if this code would work. And it does. So what have we achieved here by using bitwise operators? We reduced memory used to hold data from 256 bytes to just 32. And in Arduino world, this is massive. But this just scratches the surface. If you check this video of mine, you would see that bitwise operators are key elements for advanced way of controlling Arduino digital output and input pins. This is next level stuff. So this video, that seemed too basic and too easy at first, all of a sudden is not that basic anymore. Finally, we can look at the compound operators. The word compound means a composite of 2 or more things. Similarly, the compound operators are also a composite of 2 operators. Here is the list. Increment operator. It compounds assignment with addition. So a statement where we are adding 1 to variable a can be replaced with a statement like this. Decrement operator works the same way, but for the subtraction by 1. We also have compound for all types of arithmetic operators. Here's the one for addition. So instead of assigning to variable a the result of adding variable a to variable b, we can simply use this compound operator. We have similar compound operators for subtraction, multiplication, and division. Then we have compound parameters for remainder after division, logical OR operator, and logical AND operator. The compound operators allow you to condense the line of code. It looks more slick, but you are not really cutting on number of lines of codes, maybe with one small exception. Let's look how we can improve our code using increment and decrement parameters. First, let's create super simple program without compound parameters. We declare variable a, we open serial monitor in setup function. In loop, we run command to increase a variable by 1. And when done, we output it to serial monitor. So since at the beginning a was equal to 0 and we increased it by 1, we should see 1 in the serial monitor. Loop is running in a round-robin fashion, so each time we run it, a is increased by 1 and we should see incremented values in the monitor. Let's copy the code and try to rework it using the increment operator. In this case, we can get rid of command that is increasing the variable a by 1. Instead, we can use increment operator directly in the print function. So the code is definitely optimized here. Let's mix it a bit and test these sketches in Arduino Tinkercad simulator. Some of you might not know this, but you can actually start playing with Arduino without actually owning one, or any other electronic part for that matter. If this is news to you, you definitely want to check out my video covering this topic. So here we have the original code. Before we run it, let's open the serial monitor pane. We press start and we see 1 being displayed in the monitor. And then every second subsequent number incremented by 1 is displayed. Let's now alter the code and add the increment operator. We start the code again. This time the code works in the same way, but the sequence starts with a 0. This is because in the print function we first output the value and then increment. This can be easily fixed by changing the initial value of variable a to 1. Sheesh, that was a lot of operators to cover in a single video, which, by the way, took forever to make. Before I go, I would like to give special thanks to Dave Moreno for generous donation via PayPal, and also let you know that while I was working on this video, I gained a new patron. So by the looks of it, I cannot keep up with the support I am getting from you guys, which I guess is a good thing. I will see you in my next video. Over and out.